Section 6.3 and 6.4 in your book are a whole lot of linear algebra review, and I think it would work better if we just move on and we'll mention the linear algebra results as we need them. Also mention that in some cases, I think there are simpler ways to prove the things in section 6.3 and 6.84. For example, I don't think we actually need to use determinants, but Conway chooses to use determinants to prove some things, so we'll prove things differently. So we're skipping sections 6.3 and 6.4. We'll write down the results from there as we need them, and we're going straight into section 6.5. Now, we've already seen a little bit of section 6.5. We've seen definition 6.5.1 because this is the definition of differentiability, because it looks an awful lot like the definition in section 6.2 of differentiability, going from RP to R. Now we're just writing down the analog from RP to RQ. So this looks exactly like the definition from section 6.2 with a couple of very small changes. F is differentiable at C. If there is a linear function from RP to RQ, such that we can write f of x is equal to f of c plus our linear function. Your book likes to use A for linear functions from RP to RQ, evaluated at x minus c, and then you can add to that the norm of x minus c times f of x. And this needs to be true for all x in x, where our function capital F has the same domain and range as little f. F of c is 0, meaning the 0 vector 0, 0, 0, 0 q times in a row. And f is also continuous at C. One piece of notation you're going to see a lot in your book. We have indeed seen it in this theorem I have just written down. This script L of RP, RQ, that's the set of all functions A from RP to RQ, such that, suppose I'd better use the big line for such that A is linear under the usual vector space structure in RP, RQ, where you add and multiply by scalars component-wise. Now, I want to remind you of an example from section 5.4. So remember, section 5 is all about metric spaces. So we start with a metric space. and a function. In our case, we want a function mapping into RQ. And then we're going to suppose that is we're going to write any f of x. If x is in our metric space f of x, you can write that as f1 of x, f2 of x, up through f sub q of x, where each fk is a function with the same domain, but now mapping into the real numbers. And then your book it only proves this in one direction, but I assigned as an exam study problem both directions. If you pick a point in x, then f is continuous at that point. If and only if all of the fk's are continuous at that point. For all k between 1 and q. And we're going to use this result, and we're also going to use another similar result. We'll prove a similar result for linear functions. And we're going to use that to quickly generalize a bunch of the results from section 6.2 for functions from x into the real numbers to functions from x into RQ. So first off, I'd like to point out a little bit of notation to you. So sometimes we don't want to use this f of x as a vector. Sometimes we're going to use the fact that f of x, that is, we've seen this before, sum from k equals 1 to n fk of x times the unit vector ek. That, remember, is the vector with a 1 in the kth place and a 0 in all the other places. And it's sometimes going to be useful to have a reversed formula. That's fk of x is the inner product of ek with f of x. Remember, the inner product is you take the first components, multiply them, second components, so on, multiply each pair of components, and then add them. In this case, taking the inner product with ek, you multiply the kth component of f of x by 1, and then you add it to a bunch of zeros. So that's going to be some useful notation for us going forward. Here are a handful of basic results about linear functions that we're going to need in this section. So let's let V, W, and U be 3 vector spaces. And we're going to take 2 linear functions. A goes from V to W, and B goes from W to U. Then B composed with A, we often write that as just BA without the composition symbol. We have that if A and B are linear, then BA is also linear. Another fact, which is sufficiently straightforward that I think we will not bother with the proof of that. So let's let V, W be vector spaces. A and B are both linear functions. Then A plus B is also a linear function. And you remember how to add functions. A plus B of V, that's A of V. We often write that as just AV if A is linear plus B of V. So the sum of two functions is you just add them pointwise. Another fact is that if alpha is a real number, then alpha times A is also a linear function, is another linear function. And alpha times A is pointwise. And finally, if A going from V to the real numbers is linear, W is a vector space. And we pick a vector in W, then the function, let's say BV, that's AV times W. AV now is a real number. That is linear. You can think of this as a lot like the previous result. You're multiplying by a constant. It's just that now the constant W is the vector and the function AV, that's the function. Now let's prove a proposition about linear functions that's analogous to example 5.4.6. Let's let L be a function going from Rp to Rq, and let's let Lj of x, that can be the inner product of L of x with E sub j. So then each Lj is a function from Rp to one-dimensional real numbers. Then L is linear if and only if all of the Lj's are linear. The proof's pretty straightforward, but I feel like I've been saying, oh, this is obvious an awful lot, so let's go ahead and write out the proof. So one direction is just one line. L of x, we remember, that's the sum from j equals 1 up to q, L sub j of x times ej. And then if each Lj is linear, then Lj times a constant is going to be linear even if that constant is a vector. Then Lj twiddle of x, that's Lj of x ej, is linear. Adding two linear functions gives you a linear function. So L, which is the sum of the Lj twiddles, is linear. So that is the if direction. Now let's see the only if direction. Suppose L is linear. And let's let P sub j of x be the inner product of x with ej, so that pj of the number x1, x2 up through xq is xj. Then we have that pj of x plus y, that's the jth component of x plus y, that's xj plus yj. That's pj of x plus pj of y. And then pj of alpha x, that's the jth component of alpha x, that's alpha xj, is alpha pj of x. So each pj is linear. Then Lj, that's pj composed with L, is linear. Since we said that the composition of two linear functions is linear, something which you can check. And so that completes. Let's talk a little bit about breaking differentiable functions up into their components. Here's a proposition. Let me write this out. Let's let x be a subset of Rp, C in x, both a point in x and a limit point. And f a function from x to Rq. And then we're going to let f sub j of x be the jth component, which, remember, you can get by taking f of x inner product with the unit basis vector ej. Then f is differentiable at C. If and only if f sub j is differentiable at C for all of the j's between 1 and Q. And furthermore, we can write down what the derivatives are. df of C evaluated at any vector, that's the sum from j equals 1 up to Q. Then you take the derivatives of the fj's at the point C. Remember, df sub j of C is a linear operator. You evaluate that at V because fj is mapping into the real numbers. This is a real number, so we can go ahead and multiply it by the vector ej. And so you can write, on the other hand, if you know what df is, you can figure out what df sub j is. Df sub j of C, it's a function where if you put in the vector v, you get out the inner product of df of C of v with e sub j. So you pass from df of C to dfj of C and back exactly the same way as you pass from f to f sub j. Notice that this inner product looks exactly like this inner product with df of C in place of x, f v in place of x, and Similarly, f is the sum of the fj's times e sub j. So df of c is the sum of the dfj's of c times ej. Why don't I prove one direction of this? I'll leave the other direction as a homework or exam problem. So let's suppose that f is differentiable at c. So for some linear operator, remember we named that linear operator df of c, whose domain is Rp and whose range is Rq. We have, we'll write it like this, f of x is equal to f of c plus our linear operator evaluated at the vector x minus c. And then we add to that the norm of x minus c times some big F of x, where big F of x is 0. That's the 0 vector in RQ. And big F is continuous at C. And now we're going to let Pj be the inner product projection we saw before. So Pj of y is yj. That's the inner product of y with ej. And recall from the proof of the last proposition that Pj is linear. Then, if we take Pj of both sides, because Pj is linear, we can break it up. Pjf of x, that's Pj of f of c, plus then a Pj, the function, composed with df of c, the function, and then evaluated at x minus c. So you feed x minus c into df of c, and then you feed that into Pj. And then because Pj is linear and x minus c is a number, is just a real number, we can just write Pj composed with f of x. And remember what these things are. We've got Pj is the inner product with ej, so Pj of f of x is just fj of x. And then we've got fj of c. Then we've got Pj df of c, which remember is a linear operator. We put an x minus c. Then Pj composed with f, we're just picking out the jth component of big F. Now, f sub j of c is 0 because f of c is 0. And fj is continuous at c by example 5.4.6 by the same example we saw before. So we have that fj now satisfies the conditions of differentiability. Is differentiable at C. because fj of x is fj of c plus a linear function dfj of c equaling pj composed with df of c evaluated at x minus c, and then the norm of x minus c times a function that's 0, big F sub j, which is 0 at c and also continuous at c. So that proves one direction, and we'll leave the other direction as an exercise. So let's put this proposition together with everything we proved back in section 6.2 and see what we get. So here is a proposition 6. So this proposition, this you prove using the above proposition that lets us break things into components and put them back together, plus the proof is just proposition 6.2.11. At this point, I think you can put all the pieces together. So this says if we've got a domain in RP, f and g being functions with that as our domain and mapping into RQ, and C in X a limit point, and then if F and G are differentiable at C, the conclusion is that the derivative of their sum, that's equal to the sum of the derivatives. And in particular exists. And furthermore, if alpha is a real number, then the derivative of a constant times f is that constant times the derivative of f, in the sense of multiplying functions. Remember, df of c is a function, so alpha df of c is the function you get by you take df, you evaluate df, and then add v, and whatever you get, you multiply by alpha. And you can prove theorem 6.5.7a. This follows from theorem 6.2.12a, the above proposition, and you also need example 5.4.6. This says that if X is a domain in RP, f is a function from X to RQ, X is a point, C is a point in our domain, and a limit point. And f is differentiable at C. So df of C exists. Then you use the proposition to break down into the components, show that they're differentiable. You use theorem 6.2.12a to show the components are all continuous, and then you put it together using example 5.4.6. You get that f is continuous, at least at the point where your derivative exists. I think we'll skip the consequences of theorem 6.2.12b. Theorem 6.2.12c gives you this next theorem, 6.5.7c. We have that if X an open set of RP, C a point in X, and F a function from X to RQ, sorry. And then if F is differentiable at C, then, well, I suppose you have to use part B to get that all the partial derivatives of all the components exist. But once you do that, you can write out a formula for df of C. df of C, if you evaluate that at the vector X, say, what you get is you get the sum from J equals 1 up to Q, the sum from K equals 1 up to P, and then you can use partial derivatives. Partial K, F sub J of C, so the partial derivative at that point, and then you multiply by your coefficient xk of the vector x that you're feeding in, and then you multiply it by the vector ej. And just to remind you, this ej is a vector, this c is a vector, but everything else in this expression is scalar valued. Let's specify all the partials exists. Next up, we have that if X is open, C is in X, and F is a function from X to RQ, then the derivative is unique. There is at most one linear function that goes from RP to RQ. Linear with df of C equaling A. I could write out exactly what it means for df of C to equal A with the capital F and the norm of X minus C and so on, but I think at this point you can fill that in. Next up, we have that, remember, this one took us a while to prove, but fortunately, to generalize it, we can just go round through our proposition. So at least in an open set. We have that if partial k fj exists and is continuous at C for all j and k in the appropriate range, that is k between 1 and p, j between 1 and q, then f is differentiable at C. That derivative exists. And the last of these so we're going to let X be open and connected. So we don't just need open, we need open and connected. And f a function from X to RQ. And then if df of C is the zero function, that is, df of C is a linear operator where no matter what vector you feed in, you get the zero vector out. If that's true for all points C in our domain, then the conclusion is that f is constant. We don't have quite enough time in this video to prove the next result, which will be the chain rule. So instead, I will finish up this video by putting down a couple of useful propositions. So I suppose technically I should start with a definition. This is a definition we have seen before. So let's let V and W be two vector spaces. And let's let A be a function from V to W that is linear. Then the norm of A, there are several different definitions, but they're all equivalent. This is the supremum of the following set. This is the supremum of the set of all. You can write it as norm of AX, that's the norm of in W, divided by the norm of X, that's the norm in V, for all X in V, except you don't want to divide by 0. So that is the definition of the norm of a linear operator. And you may recall the following proposition from section 6.2. If A is a linear operator from Rp to R, then the norm of A is finite. Here is another proposition. It's not in your book, so I'll just give you the lecture number where we discussed this. This showed up in section 6.2, lecture 2, part 4. So we'll call that lecture 6.2.2.4. If A is linear and the norm of A is finite, which proposition 6.2.89 says is always true going from RP to RQ. Then A is it's continuous. Better than that, it's uniformly continuous. Better than that, it's Lipschitz. All right. So now we're going to generalize the above result to functions from RP to RQ. And we could do this the way we've done everything else in this section by breaking it up into components, but the direct proof is pretty straightforward. So let's do that. Let's let X be in RP that is not the zero vector. Then the norm of AX, that's the norm of A of, remember you can always write it vector as the components times the coordinate vectors. Because A is linear, we can go ahead and move the sum and the scalar, or xj, out front. Then by the triangle inequality, we can break that up. We can move the sum out of the norm. Our xj's get some absolute values. And then what we're going to do is we're going to use the Cauchy-Schwarz inequality. This is the triangle inequality. And this is because A is linear. And now notice that this is the norm of X times this annoying sum. So we have that the norm of A, that's the supremum of your left-hand side, divided by this norm of X. This is the least upper bound of those ratios. That's less than or equal to this A of EJ norm squared to the 1/2. And because that's the sum of finitely many numbers, p numbers, and they don't depend on X, this is indeed finite. So the norm of A is finite, and in particular, A is uniformly continuous. In fact, Lipschitz by our proposition. And I want to point out one fact about this proposition, and that's a little bit different from the one-dimensional case. If Q is 1, then the norm of A is actually going to be equal to this sum, A of ej, you can find the right vector to get you as high as this. This is often false. If Q is at least 2. In fact, the only way it can be true is if all the AEJs are parallel. That's not a fact we're going to make use of, so I don't want to go too much into that, but that is just a true statement.